GFCIs are required for all 15 amp, 120 volts receptacles located in bathrooms, garages, crawl spaces, unfinished basements, and outdoors. Yes, the GFCI is also required for 20 amp, 120 volts receptacles in the same locations. Metal electrical boxes require 2 bonding screws for mounting GFCI receptacles. GFCIs are not required for receptacles protected by other listed devices, such as circuit breakers with built-in GFCI protection. Bonding screws should be used to connect the box to the grounding conductor of the circuit. The National Electrical Code, or NEC, provides specific requirements for GFCI protection and equipment grounding. The purpose of a GFCI, or ground fault circuit interrupter, is to protect people from electrical shock. It does this by monitoring the current flowing in the hot and neutral conductors of a circuit. If there is a difference of more than 5 mA between the current flowing in the hot and neutral conductors, the GFCI will trip and cut off the power to the circuit. This difference in current indicates that some of the current is leaking to ground, which could be through a person's body. GFCI protection is required in areas where there is a high risk of electrical shock, such as bathrooms, garages, crawl spaces, unfinished basements, and outdoors. In these areas, people are more likely to come into contact with water or other conductive materials, which increases the risk of electrical shock. The NEC requires GFCI protection for all 15 amp and 20 amp 120 volts receptacles in these locations. This means that any receptacle in these locations that is used to plug in a portable appliance or tool must be GFCI protected. There are 2 main ways to provide GFCI protection for a receptacle. Firstly, you can install a GFCI receptacle in the outlet box. Secondly, you can install a GFCI circuit breaker in the panel. A GFCI receptacle is a special type of receptacle that has a built-in GFCI. It is installed in the same way as a standard receptacle, but it has 2 additional buttons, a test button and a reset button. The test button is used to test the GFCI to make sure that it is working properly. The reset button is used to reset the GFCI after it has tripped. A GFCI circuit breaker is a special type of circuit breaker that has a built-in GFCI. It is installed in the panel in the same way as a standard circuit breaker, but it provides GFCI protection for all of the receptacles in the circuit. If you have a metal electrical box, it is important to bond the box to the grounding conductor of the circuit. This will help to ensure that the box is properly grounded, which will reduce the risk of electrical shock. The NEC requires that metal electrical boxes be bonded to the grounding conductor using a bonding screw. A bonding screw is a special type of screw that is designed to make a good electrical connection. It is typically made of brass or copper, and it has a pointed tip that helps to penetrate the metal of the electrical box. When installing a GFCI receptacle in a metal electrical box, you will need to use 2 bonding screws. 1 bonding screw should be used to connect the box to the grounding conductor of the circuit, and the other bonding screw should be used to connect the GFCI receptacle to the box. It is important to consult the latest version of the NEC and local building codes for the most up-to-date regulations. Always consult the latest version of the NEC and local building codes for the most up-to-date regulations. It is recommended to have a qualified electrician perform any electrical work to ensure safety and compliance with code requirements. GFCI protection is a critical safety measure that can help to protect people from electrical shock. By understanding the requirements for GFCI protection and bonding, you can help to ensure that your home is safe. Understanding the National Electrical Code, or NEC, requirements for ground fault circuit interrupter, or GFCI, protection is crucial for ensuring electrical safety. The NEC outlines specific locations where GFCI protection is mandatory to minimize the risk of electrical shock. These locations typically include areas prone to moisture or where conductive surfaces are present, such as bathrooms, garages, crawl spaces, unfinished basements, and outdoor locations. For 15 amp and 20 amp 120 volt receptacles in these designated areas, GFCI protection is required. This means that any device plugged into these receptacles, whether it's a power tool, appliance, or extension cord, is protected by a GFCI device. The GFCI continuously monitors the current flowing through the circuit. If it detects an imbalance, indicating that current is leaking to ground, it quickly trips the circuit, cutting off power and preventing potential electrical shock. There are two primary methods for providing GFCI protection. Firstly, a GFCI receptacle can be installed directly at the outlet. Secondly, a GFCI circuit breaker can be installed in the electrical panel. A GFCI receptacle replaces the standard receptacle and incorporates the GFCI technology within the device itself. It has test and reset buttons on the face for convenient testing and resetting. A GFCI circuit breaker, on the other hand, provides GFCI protection for the entire circuit, safeguarding all receptacles and devices connected to that circuit. Bonding refers to the process of connecting metallic parts of an electrical system to create a low impedance path for fault current to flow back to the source. This ensures that in the event of a fault, the circuit breaker or fuse will quickly trip, minimizing the risk of electrical shock and fire. When working with metal electrical boxes, proper bonding is essential. The NEC requires that metal boxes be bonded to the grounding conductor of the circuit. This is typically achieved by using a bonding screw to connect the box to the grounding wire. The bonding screw provides a secure and reliable connection between the metal box and the grounding system. When installing a GFCI receptacle in a metal electrical box, it's crucial to ensure that the box is properly bonded. This involves using two bonding screws. Firstly, one screw connects the box to the grounding conductor. Secondly, the other screw connects the GFCI receptacle to the box. These connections establish a continuous grounding path, enhancing safety and minimizing the risk of electrical shock. In situations where receptacles are protected by other listed devices offering equivalent GFCI protection, such as circuit breakers with built-in GFCI functionality, additional GFCI receptacles may not be required. However, it's essential to verify that the alternative protection method complies with NEC requirements and provides adequate safety. The NEC is a comprehensive set of standards that govern the safe installation and maintenance of electrical systems. It's updated regularly to reflect technological advancements and address emerging safety concerns. Always refer to the latest edition of the NEC and consult with local building codes to ensure compliance. Engaging a qualified electrician for any electrical work is highly recommended. The electricians possess the knowledge, skills, and experience to perform electrical installations safely and in accordance with code requirements. Their expertise can help prevent potential hazards and ensure that your electrical system is properly functioning and compliant. Ignoring GFCI and bonding requirements can have serious consequences, including electrical shock, fire hazards, and property damage. Adhering to these safety measures is paramount for protecting yourself, your family, and your property. GFCI protection is not just about compliance, it's about safeguarding lives. By understanding the principles of GFCI protection and bonding, you can take proactive steps to enhance electrical safety in your home or workplace. Remember that electrical safety is an ongoing responsibility. Regularly inspect your electrical system, test GFCI receptacles, and address any potential hazards promptly. Stay informed about the latest electrical codes and best practices to ensure a safe and reliable electrical environment. Grounding and bonding are two distinct but related concepts in electrical safety. Grounding refers to connecting an electrical system or equipment to the earth, providing a path for fault current to flow safely back to the source. Bonding, on the other hand, involves connecting metallic parts of an electrical system together to create a low impedance path for fault current. The purpose of grounding is to stabilize voltage and provide a reference point for the electrical system. It also helps to protect against voltage surges and lightning strikes. The purpose of bonding is to ensure that all metallic parts of an electrical system are at the same electrical potential. This minimizes the risk of electrical shock if someone comes into contact with a metallic part that has become energized due to a fault. In a typical electrical system, the grounding conductor is connected to the neutral conductor at the service entrance. This creates a low impedance path for fault current to flow back to the source, tripping the circuit breaker or fuse and energizing the circuit. The bonding conductors are connected to all metallic parts of the electrical system, such as metal boxes, conduit, and equipment enclosures. This ensures that these parts are all at the same electrical potential, reducing the risk of electrical shock. The NEC provides detailed requirements for grounding and bonding in electrical systems. These requirements are designed to ensure that electrical systems are installed and maintained safely. It's essential to follow these requirements to protect against electrical shock and fire hazards. In addition to the NEC requirements, local building codes may also have specific requirements for grounding and bonding. It's important to check with your local building department to ensure that your electrical system complies with all applicable codes. Proper grounding and bonding are essential for electrical safety. By following the NEC requirements and local building codes, you can help to protect yourself and others from electrical hazards. Remember that electrical work can be dangerous. If you are not comfortable working with electricity, it's best to hire a qualified electrician. A qualified electrician has the knowledge, skills, and experience to perform electrical installations safely and in accordance with code requirements. Ground fault protection is a critical safety feature in electrical systems, designed to protect people from electrical shock and reduce the risk of fire. The ground fault occurs when current leaks from a conductor to ground, which can happen if a wire becomes damaged or insulation fails. Ground fault circuit interrupters, or GFCIs, are devices that detect ground faults and quickly interrupt the flow of electricity, preventing potential harm. GFCIs work by monitoring the current flowing through the hot and neutral conductors of a circuit. If there's a difference of more than a few milliamps between the current in these conductors, it indicates that current is leaking to ground, which could be through a person's body. When a GFCI detects a ground fault, it trips the circuit in a fraction of a second, cutting off power and preventing electrical shock. GFCIs are required in locations where there's a high risk of electrical shock, such as bathrooms, kitchens, garages, and outdoor areas. These areas are prone to moisture or conductive surfaces, which increase the likelihood of ground faults. There are two main types of GFCIs. Firstly, GFCI receptacles are installed in place of standard receptacles and provide ground fault protection at the point of use. Secondly, GFCI circuit breakers are installed in the electrical panel and provide ground fault protection for the entire circuit. GFCI receptacles have test and reset buttons on the face, allowing you to periodically test the device and reset it if it trips. GFCI circuit breakers have a test button on the breaker itself, which should be tested monthly to ensure proper function. When installing GFCI protection, it's essential to follow the manufacturer's instructions and comply with the NEC requirements. Incorrect installation can compromise the effectiveness of the GFCI and increase the risk of electrical shock. Ground fault protection is not a substitute for proper wiring and safe electrical practices. It's still important to avoid overloading circuits, using damaged cords, and working with electricity in wet conditions. However, GFCI protection provides an additional layer of safety that can significantly reduce the risk of electrical shock and fire. In addition to GFCIs, there are other types of ground fault protection devices, such as ground fault relays and ground fault equipment protection. These devices are typically used in industrial and commercial applications to protect equipment from damage due to ground faults. Ground fault protection is a vital component of electrical safety. By understanding how GFCIs work and where they're required, you can take steps to protect yourself and others from electrical hazards. Always consult with a qualified electrician for any electrical work to ensure that your system is properly installed and maintained. Electrical codes and standards are constantly evolving to address emerging safety concerns. Stay informed about the latest requirements and best practices to ensure a safe and reliable electrical environment. Bonding jumpers are short lengths of wire used to connect metallic parts of an electrical system together, creating a low impedance path for fault current. They're typically used to bond metal boxes, conduit, and equipment enclosures to the grounding system. Bonding jumpers are essential for ensuring electrical safety by providing a path for fault current to flow back to the source, tripping the circuit breaker off fuse and energizing the circuit. Without proper bonding, fault current can take unintended paths, potentially energizing metallic parts and creating a shock hazard. Bonding jumpers are typically made of copper or aluminum wire and are sized according to the NEC requirements. The size of the bonding jumper depends on the size of the circuit conductors and the type of equipment being bonded. When installing bonding jumpers, it's important to ensure that they're properly connected and secured. The connections should be clean and tight to provide a low impedance path for fault current. Bonding jumpers should also be protected from physical damage and corrosion. There are several types of bonding jumpers, including equipment bonding jumpers, main bonding jumpers, and system bonding jumpers. Equipment bonding jumpers connect metallic equipment enclosures to the grounding system. Main bonding jumpers connect the grounded conductor to the equipment grounding conductor at the service entrance. System bonding jumpers connect the grounding electrode system to the grounded conductor at a separately derived system. The NEC provides detailed requirements for bonding jumpers, including the size, material, and installation. It's essential to follow these requirements to ensure that the bonding system is properly installed and functioning. Bonding jumpers are an integral part of the electrical grounding system and play a critical role in electrical safety. By understanding the principles of bonding and the requirements for bonding jumpers, you can help to ensure that your electrical system is properly grounded and safe. Always consult with a qualified electrician for any electrical work to ensure that your system is installed and maintained in accordance with code requirements. Electrical safety is an ongoing responsibility. Regularly inspect your electrical system and address any potential hazards promptly. Stay informed about the latest electrical codes and best practices to ensure a safe and reliable electrical environment.